Welcome back. In this section, we're going to talk about arc length in space. So what we're beginning to study are the mathematical features of a curve's shape that describe the sharpness of its turning and twisting. One of the features of a smooth space as well as a smooth plane curve is that they have measurable length. So we're going to talk about our arc length formula, which is really very similar to our arc length formula we defined in Calc 2. We're just applying it now to a vector. So if we have some vector r with parametric components I, j, and k on a closed interval, t being on a closed interval, that arc length formula is just going to be the integral across those bounds of each the derivative of x with respect to t, derivative of y with respect to t, as well as the derivative of z with respect to t, squared and then summed under a square root integrate. So just as for plane curves in Calc 2, we can calculate the length of a curve in space from any convenient parametrization that meets these conditions here. Now, if we consider dx dt, the derivative of this and the derivative of y and then z, the derivative of our position vector, dx and y, dx dt, dy dt, dz dt, the derivative is velocity. We start with position, we take the derivative of position, we get velocity. And if we were to find the magnitude of the velocity vector, that would be essentially just finding this integrand here, the square root of the sum of the squares of these derivatives. That's essentially just the magnitude of the velocity vector. So pulling this formula in, this is just allowing me to write my arc length formula in a more succinct manner. Okay, so the derivatives, all these derivatives, the derivative of position's velocity, and then summing the squares of the components and then square rooting it, that gives us magnitude. So arc length is the integral from a to b of the magnitude of the velocity vector integrated with respect to t. Let's look at an example. Here I've brought in an example. So we have a glider soaring upwards along a helix provided by this r vector. R of t equals cosine of ti plus sine of tj plus tk. And we want to know how long is the glider's path on the interval from t equals 0 to 2 pi. So thinking about what we just mentioned, we said that the arc length is the integral from a to b of the magnitude of the velocity vector integrated with respect to t. So the first thing we need is that velocity vector. And v of t, the integral of cosine, I have sine of t, I, integral of sine, that would be minus cosine of t j, and the integral of t would be 1, so I would just have plus k. And the magnitude of that velocity vector, that is the square root of sine t squared, which is sine squared t, plus negative cosine t squared, which would be cosine squared t, plus 1 squared, which is, of course, just 1. So sine squared t plus cosine squared t, that's our Pythagorean identity. This is going to simplify to the magnitude of 1 plus 1. Sine squared plus cosine squared is 1. Or rather, the square root of 2. So the square root of 2 is equal to the magnitude of v. So that means in order for us to calculate arc length is going to be the integral from 0 to 2 pi, as those were the initial and terminal times for t. of the magnitude of velocity, square root of 2 dt. And this, of course, is a very easy integration for us. Square root of 2 integrated with respect to t becomes square root of 2 times t, which would be square root of 2 times 2 pi minus 0, or rather 2 pi root 2. So that is the length in units, whatever distance unit is specified in the problem. It was not specified here. So this value is square root of 2 times the circumference of this circle. This was a circle of radius 1. All right, in the xy plane, that's what the helix is kind of revolving around. And we have calculated the distance from our initial point, t equals 0 on the x-intercept, around this cylinder all the way to 2 pi. Obviously, the glider can keep going, but we're only measuring from 0 to 2 pi rotation. So as that glider went up into the air, made a full rotation along this helix. So let's look at one more definition about arc length parameter with a specific base point. We're going to talk about that. So considering a base point other than an x-intercept like we just had, we can find this arc length using these parameters. So given that we have some curve, and this is my curve here, right? This is C. This is a smooth curve. Parametrized by t. So each value of t, right? We might have, t equals 0, t equals 1, t equals 2, t equals 3. They're all giving me these different r vectors. So we're going to pull in this new formula here. So arc length measures a distance. S of t, we've used S to represent position before, but this is a distance from some initial time to a terminal time. And then again, we're using the magnitude of the velocity vector. But you'll notice here that there's a t. We have to use this weird looking t or tau. I'll write it kind of like this. It's like a fancy t. However you can write it. We want to avoid using a capital T because the capital T in our text means the unit tangent vector, which we're going to talk about here in a minute. So we have tau, some sort of fancy T. I will write it, just some variations. It'll probably look like that. Definitely not a 7. I always cross my 7s. All right? So anyhow, this integral I've brought in, this is just redefining the way we write our arc length, and we're using a different variable. Instead of saying from 0, we're starting at some point, maybe t equals 10, right? 10 seconds to 20 seconds as opposed to 0 to 20. Does that make sense? And because we're going to be parametrizing it, because we're going to be parametrizing it, we need to use this tau instead of our regular lowercase t. So I'm going to bring in the formula. So here we have arc length parameter with a base point t naught at p, some point at a t naught time. So it's still the same formula. We've just written it a little bit differently. And again, we're using tau as the variable of integration because t is already used in our upper limit. So we use this formula if my r of t is already in terms of some parameter t, and so s of t is representing an arc length function. We may be able to solve for t as a function of s. And so by that I mean t is now some t of s. The curve can be reparametrized in terms of s via substitution. So we'll look at that in our example. The new parameterization finds a point on the curve with its directed distance along the curve, again, from that initial base point. So not from t equals 0, some point in time. So I think it's easier if we just jump into an example. So for this next example, we're going to rethink that r of t that we initially looked at the start of this video. Cosine ti plus sine tj plus tk. We can find the arc length parametrization of the curve. I think I got it right that time. I struggle with that word. All right, so what we're going to do in this example is I'm going to come over here and say, well, if t naught equals 0, then the arc length parameter along the helix from t naught to t, using that formula we just stated, is going to be that s of t is the integral, and in this case t naught is 0, from 0 to t of v, the vector v, a function of tau. The magnitude of the velocity vector is a function of tau integrated with respect to tau. So what that means is if we think about that r vector being r of tau, and we would have cosine tau I plus sine of tau j plus tau k. And we take the derivative of that, which gives us velocity, so v of tau equals negative sine of tau I plus cosine tau j plus 1k. So all I've done was replace my t with tau. We know what the magnitude of this vector is because it's the same. So the magnitude of the v vector, the velocity vector, is going to be root 2. All right. So what this tells us now is that s of t is the integral from 0 to t of root 2, because that's the magnitude of the velocity vector, integrated with respect to tau. Integrating this, we're going to get root 2t, which needs to be evaluated. Sorry, that would be root 2 tau, which needs to be evaluated from t to 0, which gives me root 2 t minus 0, or simply root 2 t. So s of t is root 2 t. Now to simplify my notation here, I'm going to say s equals root 2 t. And I'm going to isolate my t. I'm going to divide by that root 2 and say that t equals s over root 2. So now, going back to the vector we started with, r of t, if we define t to be s over root 2, we're basically saying r of some function t in terms of s. And we can redefine that. We'll say, well, instead of just cosine t, we're going to have cosine s over root 2 I plus, then we had sine of t, so that would be sine s over root 2 j, and then plus tk, so s over root 2 k. So what we have here is the arc length parametrization for this helix. So thinking about what we've done here, we took our original position vector, r of t, and that was r in terms of time. Now we're using r of t. We've redefined it in a sense as r of s. And r of s is the position in space in terms of that distance s along the curve. So we're still finding position, but not within relation to time, but within relation to distance. We get the position of an object as a function of how far the object has traveled. Parametrizing a curve in this manner can be very useful since as time increases along that curve, the curve is traced out at a unit speed. We're going to be using some of these topics. They'll come into play later. One thing to remember is that, not every curve can be easily parametrized in terms of its arc length. But the one we were working with here, that was really easy to deal with. And so then this is a helpful use for us. As always, please email me if you have any questions. We have a couple more videos in our arc length of space curves series.